Hi everyone, my name is Vlad, and today I'll tell you about the work that I'm doing at Yale together with Leonid Glazman about transport along the quantum Hall edge that is proximitized by a superconductor. This is a pre-recorded talk, and in case you have any questions, just feel free to reach out to us. I'm leaving our emails here on the slide. I would like to start with a brief introduction. Combining quantum Hall effect with superconductivity is hard. Usually, quantum Hall effect requires very high magnetic fields of the order of several Tesla. On the other hand, superconductivity, again, usually is destroyed by such fields. However, if we make sufficiently clean semiconductor, there is a chance that there will be a window between the magnetic field at which the quantum Hall effect kicks in and the upper critical field of certain type 2 superconductors. And indeed, recently there has been a series of experiments in which superconducting correlations were induced in the quantum Hall edge, both in the integer quantum Hall regime and in the fractional quantum Hall regime. But how do we see these superconducting correlations in the quantum Hall edge? On the conceptual level, the idea goes as follows. So here is our semiconductor that is subjected to the magnetic field, and there are three electrodes. The middle electrode is grounded and it's superconducting. There is also two normal electrodes. One is upstream electrode and one downstream electrode. We inject current, we inject electrons in the upstream electrode. These electrons start to do their usual skipping orbit business along the edge in the direction of the superconductor. Then whatever passes through to the downstream electrode, we collect and see what the signal is. And the response, the current in the downstream electrode to the voltage applied to the upstream electrode can be characterized by the transconductance. So to build up expectations for what we should see in this system, let's first imagine that the middle electrode is in the normal state. For example, if the temperature is above the critical temperature. Then basically this electrode acts as a sink. Whatever we send to it just goes to the ground. Nothing reaches the downstream electrode and the transconductance is zero. Now let's say that this middle electrode is superconducting. Then the story is very much different because the superconducting electrode can only admit electrons in pairs. So for a single electron, there are two possibilities. The first possibility is sort of trivial. This electron is just not admitted to a superconductor and it passes through it. And then eventually it reaches the downstream electrode. If this type of process is dominant, then we see a positive signal. Another possibility is more interesting. Essentially, an Andreev process may happen. An electron grabs another electron from below the Fermi level, and the two hop to the superconductor together and form a Cooper pair in it. This leaves behind a hole in the quantum Hall edge, and this hole propagates towards the downstream electrode. Because the charge of the hole is opposite to that of an electron, in this case, a negative signal is observed. So let's look at what experiment demonstrates. Here on the slide, you can see a snapshot of the data from the Duke experiment, in which the setup is the closest to the simple setup that I was describing on the previous slide. This data shows the downstream signal as a function of electron density in graphene, essentially as a function of voltage applied to the gate at nu equals to 2 quantum Hall plateau. Indeed, we see that sometimes the signal is positive, indicative of the normal transmission across the proximitized segment of the edge, while in the other cases, the signal is negative, indicative of Andreev reflection taking place at the superconducting electrode. Interestingly, this data experiences mesoscopic pattern. So essentially, the signal with the gate voltage is stochastic. Another interesting part of the data is about the fluctuations in the downstream signal with magnetic field. Here is the data from the same experiment. We can see that this map on the right has vertical stripes. Essentially, if we go along if we make a horizontal cut, there are places where the downstream signal jumps abruptly. And for example, here you can see that along this vertical line, the mesoscopic pattern changes. And if we go like that, the signal jumps. So this data calls for a theoretical explanation. And we developed a theory of the mesoscopic fluctuations of the conductance with the gate voltage, which controls the electron density, and magnetic field. We considered a nu equals to 2 quantum Hall sample that is in a contact with the dirty superconductor. It is a disorder in the superconductor in our theory that leads to the mesoscopic fluctuations. We elucidated the statistical properties of the conductance and also determined the correlations in these fluctuations. The goal of this talk is to give you a flavor of our theory, and the details of the theory will soon appear on arXiv. The most basic question that needs to be addressed first is why in the first place is the signal stochastic? Why the mesoscopic fluctuations happen? And I would like to start with a qualitative exposition. Essentially, the problem that we are dealing with here is a problem about the subgap conductance of an NS junction. It is known that subgap conductance of an NS junction is determined by the interference of electron trajectories on mesoscopic scales. To see why that's the case, let's try to understand how the Andreev process happens. Let's take first one electron and assume that the barrier between the normal part and the superconducting part is weakly transparent. It is a tunnel barrier. This one electron can tunnel to the superconductor only virtually because there is an energy gap in the superconductor. And once it tunnels, it can spend only the short time in the superconductor that is determined by the uncertainty principle. If this electron has tunneled in the superconductor, it moves diffusively because the superconductor is assumed to be disordered. By the end of the allowed period of time, this electron needs to get back to the interface. There, it can grab another electron, and the two can drop to the superconductor, forming a Cooper pair in it. The amplitude of this process of transfer of a Cooper pair from the normal part to the superconducting part is essentially random because the trajectory of this electron was completely stochastic. It was very much sensitive to the particular mesoscopic landscape in the superconductor, and the length of this trajectory is by many orders of magnitude larger than the Fermi wavelength in the superconductor. So this amplitude is random. In our case, the situation is even more drastic because we have just one single conductance channel that is prolonged. The conductance in our structure is determined by the total amplitude of the Andreev processes. And this amplitude is contributed by all possible processes happening in different places. For example, there can happen an Andreev process somewhere in the beginning or somewhere at the end, or there may be like multiple Andreev processes happening along the edge. And all these partial amplitudes are stochastic, and they are also sensitive to the gate voltage and magnetic field. So the total amplitude is a stochastic variable. It fluctuates with the gate voltage and magnetic field, and essentially this is what gives rise to the conductance fluctuations. But how do we describe this complicated interference? This can be done in the following way. Essentially, the idea is to keep track of how the wave function of a quasi-particle evolves along the proximitized segment. So we start with an electron state, and then we are interested in the amplitudes that this electron is transmitted normally or as a whole. And to find this amplitude, we derived an equation describing the evolution of the quasi-particle wave function along the segment. Here is how the equation looks. Psi is a two-component number spinner, and there is a 2x2 matrix that describes how the spinner changes. The term on the off diagonal that is highlighted here is the amplitude of an Andreev process happening in a given fragment of the proximitized segment. If you look at this equation, you may notice that it is actually similar to an evolution of a spin in a magnetic field. And similarly to how we do it with spins, it is very instructive to visualize the evolution on a Bloch sphere. So here is our Bloch sphere. The north pole corresponds to the quasi-particle being an electron, and the south pole corresponds to the quasi-particle being a hole. This spin starts pointing towards the north pole, and then it feels effective stochastic magnetic field due to the Andreev processes. So how does this spin move? Essentially, it moves diffusively. Let's first assume that the edge is rather short. In this case, the spin stays close to the north pole. So the conductance is close to the ballistic one on average. There is a correction to this ballistic value that is proportional to the length of the proximitized segment. This result is just in a direct analogy to how in a diffusive process, the variance of the displacement grows linearly with time. The effective diffusion coefficient of this process is determined by the Andreev length. This is a mesoscopic length scale that characterizes the stochastic properties of the Andreev amplitude. This length scale determines how quickly the quasi-particle is converted between electrons and holes. The Andreev length can be related to the properties of the superconductor and the interface between the semiconductor and the superconductor. Here is the expression which we derived using quasi-classical approach. The Andreev length is related to the interface conductance in the normal state per unit length in the quantum Hall regime, and also the normal state conductivity of a superconductor. Quite peculiarly, this expression depends only very weakly on the superconducting properties of the metal. Essentially, the superconducting coherence length enters this expression only under the sign of under the logarithm. Actually, this fact is sort of sensitive to the particular geometry of the superconducting electrode, and here we assume that the superconducting film is much thicker than the coherence length. Okay, so this is the Andreev length, and it is an important length scale in our problem. What if the edge, the proximity segment of the edge, is larger than the Andreev length? Well, in this case, this spin evolving in stochastic effective magnetic field just completely forgets about its initial conditions, and it ends its evolution at a random point on a sphere. For example, it can end its evolution in the southern hemisphere. In this case, the electron is mainly transmitted across the proximity segment as a whole, and the conductance is negative. However, with essentially the same probability, it could have ended up in the northern hemisphere, in which case it is mainly transmitted across the segment as an electron, and the conductance is positive. The two possibilities are equally likely, so the conductance is 0 on average. At the same time, the conductance has a huge variance that is just determined by the conductance quantum. Pay attention to this 1/3 factor. It just corresponds to the averaging of the conductance over the uniform distribution on a sphere. So let's see how this prediction compared to the data. Here is again the snapshot of the data from the Duke experiment. In part, our predictions here are indeed consistent with what is observed. The signal is sometimes negative, sometimes positive, and the two possibilities are approximately equally likely. However, the prediction about huge variance is not really compatible. We see that the signal here is like 100 ohms, whereas the quantum is like 10,000 ohms. So what happens? We think that the reason for the discrepancy is that actually here we are dealing with a type 2 superconductor that is subjected to a pretty high magnetic field. So this type 2 superconductor is actually in the mixed state. There is a vortex lattice, and the cores of these vortices are just chunks of normal metal. Before, we assumed that the quasi-particle that was incident on the proximitized segment of the edge was transmitted across it with essentially a unit probability. So it always reached the downstream electrode, well, either as an electron or as a hole. However, this normal course of the vortices, they create parallel conduction channels. So the electron does not necessarily get to the downstream electrode. Also, it can just tunnel to the normal core of the vortices and get lost there. So there is only some probability with which the electron gets to the downstream electrode, which we call the survival probability. This survival probability is determined by the interface properties and also by the density of states in the superconductor at the Fermi level due to these normal inclusions. This density of states increases with the magnetic field, so this survival probability gets smaller with the increasing magnetic field. On the language of our Bloch sphere, the fact that the probability to be transmitted is no longer 1 just corresponds to a shrinkage of the Bloch sphere. This shrinkage results in the attenuation of the amplitude of fluctuations. So it's no longer a quantum, it is something smaller. However, the spherical geometry is still there. So the statistical properties of the conductance distribution remain the same. For example, the relation between the variance and the variance of fluctuation and their amplitude that I described on the previous slide, this 1/3 relation remains intact even in the presence of attenuation. Okay, so these were the basic statistical properties: the average of fluctuations, their amplitude, and also their variance. What else can we learn about them? Another thing at which we looked at is the correlations in fluctuations. So let's look at the data again. We see that this data, although it's stochastic, it's not just a white noise. So if we pick two close gate voltages, the signal at these gate voltages are pretty close by. So how do we understand something about the correlations between different gate voltages? Well, the first question that needs to be answered is why the signal changes with the gate voltage in the first place. So what changes with the gate voltage, and an important change that occurs with the gate voltage is that actually the Fermi momentum of edge states changes as the gate voltage is changed. Here is the relations. It's basically a linear relation, and of course there are some factors like the capacitance to the gate and the inverse compressibility, but it's just a linear relation. And the way to see why the change in the Fermi momentum leads to the change in the signal is to get back to this Bloch sphere picture again. So we want to compare the signal at two gate voltages, like here and here. So we want to compare the evolution of two spins on a sphere. These two spins feel the same stochastic effective magnetic field due to the Andreev processes. However, due to the difference in the Fermi momentum, there is also a constant component of the magnetic field in the z direction that is different for the two spins. So these two spins at two different gate voltages, they feel the same stochastic signal and they fluctuate in it, but also because of this constant component, the two spins diverge. So as we passed across the proximitized segment, the conductances are different in the two cases. And that is why the signal changes with the change of the gate voltage. We quantified this picture about the diffusion of two spins, we found the joint distribution function, the equation for the joint distribution function, and used it to derive the expression for the correlation function between conductances at different gate voltages. This expression is now presented here on the slide. The correlation function depends on the difference of gate voltages in a Gaussian way. And the correlation scale here that basically determines the scale at which the signals are correlated is determined by the following expression. Again, here are some prefactors like the capacitance to the gate and also the compressibility. But what's important is the dependence on the length of the proximitized segment and on the Andreev length. First, we see that quite reasonably, the correlation radius in the signal becomes smaller if we make the proximitized contact, proximitized segment larger. And this is reasonable. Essentially, the two spins have more time to diverge from each other. But what's a bit peculiar about this expression is that it has the Andreev length in the denominator. You see, the Andreev length is sort of a degree of disorder. If we perform a thought experiment in which we increase the degree of disorder in superconductors, then the Andreev length would go down. So essentially switching between electrons and holes would happen quicker. So the Andreev length goes down, but the correlation radius increases. So we increase the amount of disorder, but the signal gets smoother. And at first we were puzzled by this observation, but actually then we realized that something similar happens in nuclear magnetic resonance. There is a phenomenon called motional narrowing. So essentially, like the width of the NMR line becomes more narrow if the spin is placed in a more stochastic magnetic field. So this is kind of a neat physics that we uncovered in the correlations of the fluctuations. Finally, let's return to this data in which the signal experienced jumps with magnetic field. We agree with the interpretation in the Duke paper that probably this happens due to the entrance of vortices in the superconductor. But why does the entrance of a vortex change the signal? A way to understand it is as follows. Basically, when a vortex enters, it changes the landscape of superconducting order parameter. Basically, there appears a kink in the phase at the interface, and the width of the kink is determined by the distance by which the vortex has entered. The magnitude of the kink is 2 pi. The conductance is again determined by the interference of Andreev processes happening in different places. And it's quite clear that the change in the superconducting phase will affect different Andreev processes in different ways according to how this phase is distributed. So basically, this is why the entrance of a vortex changes the conductance, because it changes the phases of individual Andreev processes. But what can we understand about these jumps in the conductance? Of course, the magnitude of the jumps is determined by the distance for which the vortex has entered. And what do we need to compare this distance to is the Andreev length, because it is essentially a single length scale in our problem. So the jumps are determined by the ratio between the Andreev length and the distance of entrance. If the distance by which the vortex has entered is much smaller than the Andreev length, then the jump is small. Basically, the kink gets very sharp, so it's 0, 0, 0, and then almost immediately 2 pi, 2 pi, 2 pi. So this almost does not affect interference except for a very narrow window, and so the jump is small if the distance by which the vortex has entered is smaller than the Andreev length. Also, quite reasonably, if we move the vortex very far away from the boundary, it should also have no effect on the signal. And then the two asymptotics somehow interpolate in the middle, and there is some sort of a bell-shaped curve. What's a bit tricky is that the jumps themselves experience mesoscopic fluctuations, so they're also sensitive to the particular mesoscopic landscape. For example, you see that if we go along this vertical cut, the magnitude of the jump also fluctuates along this cut. So a question for which our theory can give predictions to is what is the typical magnitude of the conductance jump. To find this typical magnitude, we calculated the expectation of the squared jump. And here is our result. So we see that according to this picture that I outlined qualitatively, the typical value of the jump is small on both ends. So both when the distance by which the vortex has entered is small and large. And in the middle, it reaches the value that is of the order of signal itself, which is kind of interesting. So for the appreciable jumps to happen, the vortex has to enter by the distance of the order of Andreev length. And apparently this is a regime that is seen in the Duke data. So this brings me to the end of my presentation. We considered transport along the proximitized quantum Hall edge, and we elucidated the statistical properties of the conductance along this edge. We determined some basic statistical properties such as the average of the conductance, its amplitude and variance, and also described the correlations in the conductance. We also elucidated the jumps that happen in the conductance with the magnetic field. With that, thank you for listening to my talk. And in case you have any questions, please feel free to reach out. Bye.